Welcome to Study Loop.
Problem 57 asks, given the following information, how you would make each solution. So part A here asks how you would make 100 milliliters or 1.00 times 10 to the second milliliters of 0.5 molar potassium chloride. So remember that this capital M here, or which stands for molarity, is telling you to think about how many moles of solute, or the thing being dissolved, there are per 1 liter of solution. So in this case, it's 0.5, half a mole of potassium chloride and 1 liter of solution. So the way that we can figure out how to make this solution is simply by knowing, by looking up the molecular weight, shortened as MW, of potassium chloride. You can either look this up on Google, or you can do the math based on the atomic masses of each potassium and chloride and add those together. But what you get is 74.55 grams per mole. So what we know then is we have 0.5 moles of potassium chloride per 1 liter of solution. We know that we eventually want to figure out how many grams of potassium chloride we need to make this solution, so we can plug in that molecular weight. We eventually want to figure out a reasonable number of grams to put in milliliters of solution, not liters. So we can convert from liters to milliliters by knowing that there are 1,000 milliliters per liter. And then we know that we ultimately want 100 milliliters, or 1.00 times 10 to the second milliliters of this solution. So once all of these other units cancel, what that leaves us with is the number of grams we'll ultimately have to add to the beaker or flask or whatever to make a 0.5 molar potassium chloride solution. So what this ends up being is 3.73 grams of potassium chloride that you will want to dissolve in enough water to total 100 milliliters. Part B here asks how you would make 1.00 times 10 to the second grams of a 0.5 molal potassium chloride solution. So unlike the capital M before, this is a lowercase m, and what that means is the number of moles of solute per kilogram of solvent. So unlike before, the denominator here isn't talking about the total solution, but the actual solvent dissolving your solute. And so this particular math is a little bit more complicated because you have to do a little bit of extra algebra to figure out the proportions of solute and solvent that give you the proper mass of your whole solution, while still giving you this 0.5 molal ratio. So what I'll do here is I'll set up a couple of different equations that we can then solve to figure out the number of grams of both solute and solvent that we need. So we're going to call the mass of potassium chloride X, and the mass of water, the solvent here, Y. And what we'll ultimately need to find is mass of potassium chloride and water that gives us a total of 100 grams. The other equation that we'll need is the actual molality equation. So I'm going to call the number of moles of potassium chloride here capital A. I'll call the number of kilograms of water this capital B here. And we know that ultimately our molality is going to be this A over B. So what we can do here is take this part first and do a little bit of conversion by using the molecular weight of potassium chloride, sorry. So we know eventually that we want X number of grams of potassium chloride. And we know the molecular weight of potassium chloride. We know that 1 mole is 74.55 grams. And so that gives us X over 74.55. We also know that we have this relationship down here of X plus Y equals 100. And so what I'm going to do is I'm going to set everything up so that it's relative to Y in order to plug back into this equation and solve for X. So we know that X then is equal to 100 minus Y. And we can substitute that in for this equation here. Okay, so that's the A portion of this. Now B, the number of kilograms of water. We know that we have Y grams of water over here. And we know that we eventually want that to be in terms of kilograms. So we can set up that conversion by knowing that there are 1,000 grams per kilogram, which gives us Y over 1,000. So like I said, I have both of these terms now in terms of Y. So what we can do first is plug in our A and B factors into this molality equation. So A is this 100 minus Y over 74.55, and that's over our Y, or our B component, this Y over 1,000 here. We can simplify this by multiplying this whole right-hand side by 1,000 over 74.55 to cancel out each of these denominators. And what that leaves you with is 1,000 times 100 minus Y on the top over 74.55 Y on the bottom. Finally, we can plug in our known molality, so 0.500 molal. And we can solve for Y. So what that gives us is Y equals 96.41 grams of water. And we can plug this back in to this equation over here. To find that X then, or the number of grams of potassium chloride, is 3.59 grams. So what this means in terms of describing how to make this solution is that to make a 0.5 molal calcium chloride solution, we have to mix 3.59 grams of calcium chloride with 96.41 grams of water. So somewhat simpler is this percentage by mass idea of concentration. And so what this means is that this is the number of grams of solute per 100 grams of solution. So what this means is that for every 100 grams of calcium chloride solution, there are 5 grams of pure calcium chloride. So in this case then, like I just said, 5 grams of calcium chloride for every 100 grams of solution. We know in this case that we want to make 100 grams total of solution, or 1.00 times 10 to the second grams. So we can multiply by that. What that tells us is we need to mix 5 grams of calcium chloride then, or potassium chloride, sorry, with 95 grams of water, the solvent, to give us 100 grams total of solution, 5% of which is potassium chloride.